Okay, hi everyone, and welcome to the next episode of Extremal and Probabilistic Combinatorics webinar. Our today's speaker is Stefan Glock, who will try to fight the technical issues that comes with the online talking, and also he will fight with long induced path in sparse random graphs. So maybe before just one more technical remark. During the talk, if you have a question to Stefan, you are more than welcome to unmute yourself and just ask your question, or type your question in the chat, and one of the organizers will forward the question to Stefan. Okay, I guess now that's everything. So Stefan, the virtual stage is yours.
Thank you, Hansa. Thank you for the introduction, and thank you everyone for joining today. So yeah, I want to talk about a very natural unsolved problem in random graphs. So many experts in random graph theory have worked on this, but we still don't know the answer. Okay, so this is the problem. We look at the usual binomial random graph where we have n vertices and each possible edge appears with probability p, which I denote here by d over n. And I will mainly focus on the sparse regime. So here d is just a constant. We assume it's greater than 1 so that we're in the supercritical regime. Okay, so the question that we want to investigate is, what is the length of a longest induced path, right? And the main result in this talk that I want to share with you is an improvement in the lower bound for this problem. Okay, so formally, let's denote by L of G the maximal order of an induced path in G, and similarly by T of G, we denote the maximal order of an induced tree in G. So trees were actually studied earlier, so we will first learn something about the results for trees. Okay, so let's look at the problem for induced trees. The starting point for this is the following result due to Erdős and Palka from the 80s, who considered the dense regime. So P, the edge probability, is a constant, and they showed an asymptotically optimal result with high probability, which here means always that the probability tends to 1 as n tends to infinity. The order of an induced, the maximal order of an induced tree in this random graph is asymptotically 2 times the logarithm, where the base is this 1 over 1 minus p of np. Okay, so the experts among you will notice that this quantity here is also the independence number of G and P, which was already studied much earlier. And we will see during the talk how these two problems are related, these induced trees and the independence number. Okay, so to give you a flavor of these numbers, where this funny logarithm comes from, let me show you how you can prove the upper bound. This is actually not so difficult, and it just uses the standard first moment method. So we let set denote the number of induced trees of order k, and for k here we pick something which is just a little bit larger than this value. And now we want to compute the expectation of set. Okay, so let's do this. We have n choose k ways to choose a tree. Then we have k to the k possibilities. So sorry, we have n choose k ways to choose a set of size k. Then we have k to the k possibilities to pick a tree. Now this tree has roughly k edges. So we get a factor p to the k for the edges. And we have roughly k squared over 2 non-edges, which gives us this 1 minus p factor. Okay, so now we combine these terms and plug in the value of k, do some simple calculations, and then we see that this expectation tends to 0. Okay, so I was a bit quick here, but the point is just it's simple. You just compute the expected number of these induced tree, and basically a union bound tells you that with high probability there can be no larger one. Okay, so
Excuse me. I just have a really quick question.
Yes.
So since the number of trees should be k to the k+2, right? So then do we just ignore the exponent of 2?
Yeah, I mean, it's k to the k-2, I guess. This is
-2, that's right.
Sorry. So it's an upper bound, but I'm just doing this roughly here, very roughly. Okay.
Thank you.
Cool. Yeah, so the lower bound uses the second moment method. It's a little bit more complicated. I don't want to do it here, but yeah. So what I want to discuss is the sparse regime. And this was initiated, this was asked for by Erdős and Palka. So they here's again their result in the dense case. And they asked what happens in the sparse case when the edge probability is just p being d over n, and d here is constant. So note that when p is small, when p tends to 0, one can rewrite this logarithm a little bit nicer. So this is what I will do here also. I will mainly work with this expression, which is 2 times n over d log d, which is asymptotically the same. Okay, so it turns out that the first moment calculation still works. I actually showed you the general one. So basically for the whole range of p, the first moment method tells us that an upper bound is 2 n over d log d for the size of this induced tree. Unfortunately, the second moment method does not work in the sparse case. And this is why the problem is interesting. And this is why Erdős and Palka posed this conjecture. They said for any d greater than 1, one should show that with high probability there is just, I mean, at least a linear induced tree. Okay, so because we're in the supercritical regime, we know there's a giant component which has a spanning tree. But what we're asking for here is an induced tree that has linear size. Okay, so here's the conjecture again. And actually this was proved quite soon in the late 80s by various groups, Fernandez de la Vega, Frieze and Jackson, Kuchera and Rödel, and also Luczak and Palka proved this conjecture. Maybe the strongest result was from Fernandez de la Vega, who showed that this constant C over D here, C of D here, you can take it to be asymptotically log D over D. So this is already within a factor of 2 of the first moment upper bound. Okay, so what's next? What else can we say here? All right, so one natural question from there is, can we say something about specific induced trees? So for example, paths. And this was studied also by Frieze and Jackson around the same time. They show that with high probability, you can actually find a linear induced path. Okay, so 2 slight blemishes of their result were that they needed D to be sufficiently large for their proof to work. And also the dependence here of this new constant C tilde of D, it was far from optimal. But this was rectified actually a little bit later by Luczak and independently by Suen. So they showed 2 things. First of all, the result holds for all D greater than 1. So this conjecture of Erdős and Palka actually holds for paths, not only for trees. And the second thing they showed is that you can also have this dependence here to be asymptotically log D over D. So this too is within a factor of 2 of the upper bound. All right, so then the other natural question, of course, is what is the optimal result, right? So we have here this inequality. Again, T is the size of the largest induced tree. L is the length of the longest induced path. Of of course, every path is a tree. So we have here this trivial inequality in the middle. We have the upper bound 2n over d log d, which just comes from the first moment method. And we have a lower bound, which is half of that. Okay. We want to know what is the truth. Now, because I said the second moment method does not work in the sparse case. So this lower bound is proved using a different method. In fact, these proofs that I mentioned, they all are kind of constructive. So you start building or growing a tree and try to enlarge it. Okay, I want to argue that using such a constructive approach, you can probably not beat this lower bound. So it's what we call an algorithmic barrier. Okay, so why is this? Suppose we grow our tree somehow step by step by trying to attach new vertices, and if we cannot do this anymore, we abandon our current tree and try to build a new one. And then we can analyze this algorithm. And let's look at the point when the tree reaches this critical size n over d log d. Now look at one vertex v in this tree, and we want to ask ourselves how many vertices w are there which have this edge back to v, but no other edge to the tree. Okay, so if we could attach this vertex w and still have a larger now induced tree. Okay, so let's compute the expected number of these vertices w. So we have of the order n many choices for w. We want this edge from w to v, which gives us a probability p, but we don't want any of the other edges. So this is this 1 minus p to the order of t. Now 1 minus p is roughly e to the minus p. We plug in this critical order of t, do some simplification, and see that this expectation is 1. Okay, and if the tree is a little bit larger than this, then this expectation will drop far below 1. And this is all just a heuristic. It's not a proof, but it's an indication that such a method will not allow you to build a tree that has size much larger than n over d log d. And this is also reminiscent of such algorithmic barriers in many other problems. Maybe here's a major open problem, if you want to think about it. Is there any efficient algorithm that finds an independent set in GNP whose size is a little bit larger than n over d log d? So again, n over d log d you get with an easy greedy algorithm, but can you beat this just by a little bit? There is evidence that actually this is not possible. And here a similar thing seems to be going on.
Can you, Stefan?
Yeah.
Can you remind us which regime this we are in?
Okay, so it's so sorry for the remainder of the talk. I will always be assuming that p is d over n and d is a constant. So we are in the sparse regime where the average degree of the random graph is constant. Okay.
Yeah, and if we remove the induced part, the problem. Gets
well, no, so the inducedness here is important. These non-edges have a significant effect. Obviously, for the independent sets, here we have to also insist that none of these edges are there, right? Yeah. Okay, so we will see later in some calculations where really this inducedness has a significant effect on the problem.
Okay.
Okay. Yeah, thank you for the question, and please feel free to ask more if you have any. Okay, so I mentioned that there is this algorithmic barrier also for independent sets, but of course for independent sets we know the answer. This is for the existence, so for the independence number, we know by this classical result of Frieze that the independence number is asymptotically 2n over d log d. So here we have this additional factor 2, which matches the first moment upper bound. Okay, and his idea was to combine the second moment method, which on its own does not work, with concentration. And we will use also this method. So let me, I will not give the proof here, but I want to show you how you can prove it. It's a nice trick.
Sorry, Stefan, just
Yeah.
that I remember or recall, when you say asymptotically, you also mean only when D is fixed but large, right?
Yes, so this exactly, the limits tends to 1 as D tends to infinity, but for the proofs we assume that D is large. So the precise statement would be for any epsilon greater than 0, there would be a D0 such that whenever D is larger than D0, then the independence number or the induced tree or whatever is 2 plus minus epsilon times n over D log D. Okay, yeah, good question. Good. Okay, so here's a general setting, not only for this independence number, but really you can maybe apply this for a lot of problems. Okay, so suppose you have a random variable x, and your aim is to prove that with high probability x is at least something, at least b minus t, where b is your actual target value and t is a small error that you're happy to live with. So now suppose you know two things. Suppose first you know that the probability of x being at least b is at least some rho. Now rho can be small, it can even be exponentially small. So such things you might still get using the second moment method. So when I say second moment method does not work, I mean it doesn't give you a with high probability result, but it might still give you some small probability. Okay, so now suppose you can complement this with a concentration inequality. So you have an upper bound on the probability that x deviates from expectation by a lot. And what we need here is that this probability in the second inequality beats the probability that we have in, say, the second moment bound. Now suppose that we have these two things. So the second one this is a concentration inequality we can get, say, from Azuma, Talleyrand, or your favorite concentration inequality. Now we can combine these two things. So we can concatenate the two inequalities to compare the two probabilities, and then by monotonicity of the probability measure, we can see that b, this target value, can be at most the expectation of x plus t over 2. Right? And now we can plug in this additional information to bound the probability of our bad event. So we want to say the probability that x is less than b minus t is small. We plug in this additional information, and then we again apply b. So we use both tails of the concentration, one tail to compare the two probabilities, and then the other tail to actually bound the probability of our bad event. And then we see that this probability is small and we're happy. Okay, so this is maybe what you can take away if you haven't seen this, is really this observation of Frieze, that you can combine and you can make the second moment method work, even in cases when it might not work at first sight. Okay. Good. So using this result of, so one remark why concentration occurs is that the independence number is 1 Lipschitz. So if we think of our G and P, this random graph, as a product probability space, and we view it as a product over the vertices, then 1 Lipschitz means when you change edges only at one vertex, then it can change the independence number by at most 1, because maybe you add an edge which destroys your or you have to delete one vertex from this largest independent set. Maybe you gain one, but it cannot change by more. So this is what I mean here by 1 Lipschitz, and then Azuma's inequality gives you concentration. Okay, so using this result of Frieze, which is about independent sets, Fernandez de la Vega obtained the optimal result for induced trees. So he got this additional factor 2 here. So the order of a largest induced tree in GNP is asymptotically 2 n over d log d. And the proof is quite nice and short once you have these other results. So let me show you how this works. We do a 3-round exposure of the random graph. So we reveal the random edges in 3 steps. And in each step, we have a with high probability result. Then we can condition on whatever we have and continue. And if in each step we have things with high probability, then we get in total also with high probability. Okay, so in the first step, we reveal the random edges inside V1. And here we apply one of the earlier results. So we just want an induced tree, which we call T0, whose size is n over d. We know we can even get n over d times log d, but we don't need it. So we just take an induced tree of order n over d. And now we fix this. So this tree is now fixed. Now in the second step, we look at the edges that go across. So we reveal all the random edges across. And what we are interested in is the set X on the right-hand side, which consists of those vertices that have exactly one neighbor in T0. So we want them to have exactly one neighbor in T0 because these are the vertices that we could attach to the tree. So they would be leaves in the tree. And now you have to do some calculations, but every vertex on the right-hand side has a constant probability, constant probability to be in the set X. And because they are independent, it's easy to see that with high probability, this set X has still constant size, maybe say n over 10 or something. So you only lose a constant factor here. Now we fix this thing. So this also holds with high probability. And then in the third step, we reveal the random edges on the right-hand side inside V2. Actually, we're only interested in those which are inside X. And what we want to find here is an independent set. Okay, so if we find an independent set, that means we can attach all these vertices to our tree. They all have exactly one neighbor. And because it's an independent set, they don't have any edges among themselves. So it will be an induced tree. And this is where we apply Frieze's theorem. And maybe let me go back here to convince you that I'm not cheating. So we have this 2n over d log d. And now because we lose x is much smaller, n changes. But this is no problem because, I mean, you reformulate this result as 2 over p times log np. And p has not changed, right? P is just the edge probability. This has not changed when we apply Frieze's theorem. Only inside a logarithm, we have a loss of a constant factor, but because it's inside a logarithm, it doesn't hurt us at all, okay? This is just a side remark. Okay, so Fernandez de la Vega has this really nice result. It extends this result of Erdős and Palka to the sparse regime. And he asked whether one can also improve this algorithmic bound n over d log d for paths. So note that his proof gives you something which is very much not a path. Basically, the majority of your vertices in this tree that you get in the end are just leaves, okay? So this does not work for paths. Okay, so this was his question. Can you maybe somehow else improve the bound for paths? And this is the main theorem that I want to present and tell you more about. Okay, so this is what we prove. With high probability, there is an induced path in GNP whose size is at least roughly 3 over 2 times n over d log d. Okay, so we have this improvement on this algorithmic bound. Unfortunately, we cannot prove this with 2. What we want to get in the end is 2n over d log d. Unfortunately, I cannot prove this, so it's kind of halfway. Okay, so the proof consists essentially of 2 steps. in the first step, we want to find many disjoint paths who together form a large induced subgraph. For this, we will also use this combination of second moment method and concentration. And then in a second step, we want to connect these, or say almost all of these paths into one long induced path. So for this, we will use the depth first search framework. But so maybe before I discuss more about the proof, are there any more questions about the result? So because Hansa asked, I should say this little O of 1 here is also depends on D. So this is this epsilon, and then D has to be sufficiently large. Okay. Okay, so if there are no questions on the result itself.
I have a question.
Yeah, yeah.
So can you also, I mean, like looking forward, can you also guess something like there's a large induced copy of all trees of a certain size or something like that?
Sorry, can you repeat the question?
Can you guess something somewhat bold, like there's a large induced copy of every tree or something like that?
You're too quick. We will come to this, okay? So I will mention this. We'll come back to this in the end, okay? Yes. So far the result is just for paths, but so the question for general trees we will discuss briefly in the end. Any other question? Okay, so then I can say something about the proof. Okay, so the first step, we want to find this induced forest whose components are long paths. The starting point for this is the following theorem, recent result of Cooley, Draganich, Kang, and Sudokov. And they considered induced matchings. And they showed with high probability, the order of a largest induced matching is 2n over d log d, is again asymptotically optimal. Again, the upper bound is a simple first moment calculation, and for the lower bound, they use this combination of second moment method and concentration. And essentially, the reason here why concentration occurs, so remember for Frieze's result, we use that the independence number is 1 Lipschitz, meaning that if we change edges at one vertex, it can only change our random variable by 1. And here, if you look at induced matchings, and you let's say x denote the size of the largest induced matching, then this random variable will be 2 Lipschitz. So if you change edges at one vertex, maybe you lose one of the edges of your matching, maybe you gain one, but not more can happen.
So Stefan, here the order is in vertices rather than edges, correct?
Sorry, can you repeat it, please?
You count the order of the matching in terms of vertices rather than edges.
Sorry, yeah. So when I say order, I mean the number of vertices. So this matching will have roughly n over d log d edges, which gives us 2n over d log d vertices. I phrase it in terms of vertices because then we always have the same number 2n over d log d, which we will also see in the coming results, okay? So here we have already one. So for the first step of our proof, what we do is we generalize this result to forests with larger components. So you can think of an induced matching as an induced forest where every component is a single edge. But then you can ask, okay, what if I not have a single edge, but some fixed tree? And this is a byproduct of the proof. Yeah, you can take any fixed tree T, and then with high probability, when you look at the largest induced subgraph in your random graph, where every component is a copy of T, then this will have order roughly 2n over d log d. Okay, so when T is here just a single edge, then it's the result of Cooley, Draganich, Kang, Sudokov. Okay, but so actually we need more. The crucial thing here is that we can even find such an induced forest where the components are paths and their length is polynomial in D. Okay, so this is this lemma here, which is essentially the first step of the proof. Okay, so the step when we find these many somehow long induced paths. So with high probability, when we can find an induced forest of this optimal order 2n over d log d, where every component is a path of length L, and here L is roughly square root d. This is important that we have here this polynomial length of the paths. Okay, so let me mention how we can prove this. It's exactly this combination of second moment method and concentration. So using the second moment method, we can show that if you take any bounded degree forest of this order 2n over d log d, then it will be an induced subgraph of G and P with some probability. It's very small because the second moment method on its own does not work, but it's something. It's this e to the minus some constant, and then, okay, n over d squared log squared d. You don't have to, I can't give you now intuition for this bound. I just want to say it's very small. It's exponentially small, but you can get it. So if we now say x is a random variable, which denotes the maximal order of an induced forest, where every component is a path of length L, then just reformulating the lemma, we have this type A inequality that tells us the probability that x is at least our target value is at least, say, rho. So we let rho denote this exponentially small probability. Okay, so this is just what follows from the lemma. This is what we get from the second, not from the lemma, sorry, from the second moment method. Okay, so here's this one type A inequality again. So now we want to complement this with a concentration inequality. And this is the reason why in the first step we only find small paths. So they are kind of long, but they're still small because we need a Lipschitz condition. So remember, for independence number, we were 1 Lipschitz. For induced matchings, we're 2 Lipschitz. Now when our components have order L, then we're L Lipschitz, because if we mess up the edges at one vertex, we might destroy one of our components, we might gain a new component, but not more can happen. So this random variable x is L Lipschitz, and then using concentration, I didn't write down here a specific concentration inequality. Usually what you get is the probability of x deviating from its expectation significantly, say by an epsilon fraction, is exponentially small, and the order of the exponent will be roughly this expectation divided by the square of the Lipschitz constant. Okay, so this is just the usual what you get from concentration. And what we need is that this bound is better than the second moment bound. Okay, so we look at this exponent in the concentration bound, and we need this to be larger than the exponent in the second moment bound. And this is the case as long as we pick L squared to be much less than d over log d. Then we get the second type B inequality, which is better than type A. And we can combine it, as I sketched when I mentioned Frieze's result, to show that x is large or has our desired size with high probability. Okay, so this point here that L squared needs to be less than d over log d is just, this comes from the Lipschitz constant, and it's the reason why in the lemma we get this square root d. Okay, this is the connection. Okay. Are there questions to this part? This is the kind of the first step where we find these many long paths. Okay, so then let me explain how we can do the second step. So here our goal is to connect these paths. So again, we do this multiple exposure argument. We first find in one half of our random graph, we apply this lemma to find an induced forest, call it F, which consists of many induced paths. So it's induced and it consists of many paths, which have size roughly square root d. Now fix this induced forest F, this will be fixed. Now we expose the remaining random edges that go across and inside V2. And what we want to find are connections, right? So we want to go from one path via V2 to the next path, follow this path, and then somehow jump to the next one, okay? And kind of combine these paths into one long path. Now you have to be careful, because if you just take two paths, P1 and P2, the probability that you can actually connect them is really small. So you cannot insist on, say, connecting specific paths together. You have to do it somehow systematically. And the way how you can do it is using an auxiliary digraph. So we define this digraph D, whose vertices are exactly the components of F. So every path, every component path in F will now be a vertex in this auxiliary graph. And edges in this auxiliary digraph will tell us whether we have a suitable connection between two paths. Okay, so this digraph is random because we define it when we reveal these edges across and inside V2. Okay, so let's look at this auxiliary digraph in a little bit more detail. So again, the vertices of this auxiliary digraph are just the components of F. And now, how do we define the edges? So suppose we have two paths here, and actually we give them an orientation. This is just, you can pick this arbitrarily and then fix it. It just tells you how you want to traverse your paths. So let's take P1 and P2. Now look at the last epsilon L vertices of P1. So we don't insist necessarily that we use all of the paths. We cannot hope to jump from the last vertex of P1 somehow to the first vertex of P2, but we look at the last segment of P1, then the first epsilon L vertices of P2. Now we want to somehow jump from between them. So we want to find this vertex A, which is in this new set V2. We want to have an edge from A to the last segment of P1 and an edge to the first segment of P2. But we don't want any other edge to F, right? Because we want to have an induced path in the end. Okay, and if this is the case, if we have such a connecting vertex A, then we include P1, P2 as an edge in our auxiliary digraph. So this auxiliary digraph now is for us a model how we can connect these individual paths into one long path. And what we want here, our aim is to find an almost spanning path in D. So in this auxiliary digraph, we want an almost spanning path. Because if we have it, it tells us, so we can start in P1, go traverse P1, then we know there's some connection to the next one, P2. We can follow P2 and then again use one of the edges in, or follow the path basically in D, which tells us how we can combine the paths.
So Stefan?
Yes.
So this auxiliary digraph, it actually, I mean, it's a simple digraph, right? There is no directed cycle of length 2.
No, there could be, but it's not an issue. I mean, you can have this connection also at the other side. You can also jump to P2 to be right.
Oh, okay, I see. Okay, thanks.
So, are you fixing the directions of these paths before you make the graph?
What do I fix?
The directions of these paths.
Yes. So the directions of the paths are fixed, but you can pick them arbitrarily. So you first fix the forest, then every path in the forest gets an orientation. This is fixed, and then you define how you have a connection. So you always want to jump from the end of one path to the initial segment of another path. So that in the end, when you connect all of them, you're consistently when you kind of traverse through the paths. But this orientation is just a technicality. It's really not an issue. You can think of this as a normal, simple graph, but formally it has to be a digraph. Okay.
And Stefan, do we require from your connecting vertex A to be connected only to the suffix of P1 and prefix of P2, and not to any other vertex in the union of the passes?
Yeah. So I want this edge from A to this last segment of P1. I want an edge from A to the first segment of P2, but I don't want any other edge, or not, I don't only want it, but I insist that there is no edge to the rest of F. Okay. And actually, now that you're saying it, to be more precise, we also need that these new connecting vertices form an independent set, right? So this definition of an edge ensures that A only has the correct edges to F, but when we add all the connecting vertices in the end, they also have to form an independent set so that we get an induced path. This is a slight technicality that I brush over here. So basically, you need to find this almost spanning path, but it's actually what you need to find is a conflict-free almost spanning path, but I don't want to go into the details for this. Unless, I mean, we can discuss in the end if someone really wants to know more about this, we can discuss. But for now, suppose I have this random auxiliary digraph D, and we want to find an almost spanning path in this auxiliary digraph. Okay. And if we can do this, we get our long induced path in G and P. Now, the intuition is that because this auxiliary digraph is defined randomly, it's defined when we reveal the random edges. It's kind of random-like. It's not an ideal random graph. So here, P1 and P2, the probability that I have this connection is not independent of the other events. So it's not a nice random graph, but it's similar to this, okay? So let's assume for now that it is actually a nice random graph. Then we have results, classical results in random graph theory that tell us if we have a random n-vertex digraph, and we want to find an almost spanning path, then we have this with high probability if the edge probability is much larger than 1 over n. So again, I kind of stating it not in the most precise way. So you think you have your edge probability is some big constant over n, and the bigger your constant is, the tinier is your epsilon. This is kind of almost, so the fraction of vertices that you're not covering, okay? And when C tends to infinity, then epsilon tends to 0. Okay, so this is old, but actually there is a nice way to prove this using depth first search. And there is a paper of Michael Krivellevich and Benny Sudokov who demonstrate very impressively how you can use this simple depth first search framework to prove not only such a result, but also phase transition and this kind of thing. So I really recommend reading this. So, okay, so this is the thing. When the edge probability is much larger than 1 over n, then using depth first search, we can prove in a random digraph that we have an almost spanning path. Now we cannot use these results directly as a black box because we don't have an ideal random graph, and there's also this issue with the connecting vertices forming an independent set. But the point is we can use the method. So we just look at how they prove using depth first search that there is such an almost spanning path, and we have to look what the proof gives us in our setting. Okay, but so what I haven't told you is why the edge probability is much bigger than 1 over n. This is the kind of crucial heuristic that you should check, right? That you can hope that there is an almost spanning path. Okay, so let me explain why this random auxiliary graph has the desired edge probability. Okay, so again, the vertices of this auxiliary graph are the components of F. So now I'm assuming that the order of F that we're aiming for here is C times n over d log d. So C here is an unspecified constant. In the end, ideally, we would like this to be almost 2. We can't quite get it, but we will see why. But for now, it's just some constant, okay? So how many vertices does the auxiliary digraph have? So let's denote this by n. Then this will be roughly n over dl. So I'm even ignoring not only the C, but even the log d. It doesn't play a role in the order of the induced of this auxiliary digraph. Okay, so the order of our random graph is roughly n over dl. Now let's compute the edge probability. So we have again this picture here that tells us when we have an edge between P1 and P2. So let's compute with what is the probability actually that we have this edge. Okay, so if I look at one fixed A, so I fix A, and I ask what's the probability that I have the right edges. So I want an edge from A to the last segment of P1. So for this, I have epsilon L possible vertices. Actually, epsilon is just a small constant, so let's ignore it. So I have of the order L vertices that I might connect to, and I need one of them, which happens with probability P. So roughly speaking, it's just a heuristic. I have probability L times P for having this edge from A to P1, okay? I have the same probability for having an edge from A to P2. So now we don't want any of the other edges, okay? So this also has a significant contribution. So we have this 1 minus P, which says non-edge to all the vertices which are already in our induced forest F. So this is roughly e to the minus P times, we plug in the order of F. And here is the point where this constant C is crucial. So P times n over d cancels, e to the log d is just d, but what we are left here with is the term d to the minus C. This is the point where the non-disinducedness comes in. Okay, and finally we have n over 2 possibilities for the connecting vertex A. Okay, so in total, as an estimate for the probability of having an edge is LP squared for the probability of having the two edges that connect us, d to the minus C for the probability of not having any of the other edges, and n for the number of possible connecting vertices. Okay, so now we plug in P is d over n, and then we also substitute the order of the digraph, right? So we need edge probability to be much bigger than 1 over order of the random graph. The order is this n over dl. If we plug this in here, what we get is in the end L times d to the 1 minus C divided by n. Okay, and we need this to be much bigger. So we need a numerator to be much bigger than 1. So we need L times d to the 1 minus C to be much bigger than 1. And now we see how this connects to the first step, right? L is the length of these paths that we find in the first step. And there we had this lemma, which told us that we can find path of length square root d, roughly square root d. So we have an exponent 1/2. So we can choose C to be a little bit less than 3 over 2. And then this heuristic will still tell us that our edge probability is much bigger than 1 over n. And you can make this rigorous. I don't have time to explain how to make this rigorous, but this is the whole heuristic. So this is essentially what I wanted to tell about the proof. Since we have a little bit of time left, let me just summarize it again. I think it often helps to summarize things. And in this time, you can also think about questions. And then I will mention some open problems in the end. Okay, so a brief summary. Maybe I start here from this inequality, which kind of captures the starting point. We have these two things: longest path, largest induced tree. We have an upper bound coming just from a first moment computation, which is 2n over d log d. We have a lower bound, which is half of that. Probably using constructive methods, we cannot improve the lower bound. So how can we improve it? there's this nice combination of second moment method with concentration. And Fernandez de la Vega used this to get the optimal result for trees. So this problem is now settled, but his proof does not work for paths. So he asked, can you improve this half of the upper bound for paths? This is our main result, that we can improve it halfway towards the optimal bound. And we use these two steps. In the first step, we find many kind of short paths, but not too short, using, again, this method of Frieze. And then using depth first search, we want to connect these paths into one long path. The starting point for this was this recent result of Cooley, Draganic, Kang, and Sudakov, which we generalize. And here we have this lemma that tells us, yeah, we can find this induced forest, which already has some path of a certain length. And what we got was square root d. And the reason why we got square root d was just the Lipschitz constant. We need our concentration bound to be better than the second moment bound. And we just picked the optimal value such that it still works. Okay. Right. And then I showed you how you can connect these paths using depth first search modeled by this auxiliary digraph. And in the very end, we saw here the connection, what we need for L and for C. And if this lemma would be true, if we could find path in the first step, not only of length square root d, but maybe d to the 1 minus little of 1, then we see here that we could pick this constant c to be almost 2. So it would settle the problem. And this is not, so you can make this rigorous. This connecting step works exactly the same way. If you can find longer paths in the first step, you get a better constant when you do the connection. Okay, so let me conclude with some open problems. The first obvious problem is to improve this constant 3/2 to the optimal one, which would be 2. I already now told you one way to do this is to just improve the length of these paths in the first step. So I get roughly square root d. If you can get almost linear in d, it would immediately solve the problem. So that would be nice. And then, so there was this question during the talk, which I think is this one, if I'm not mistaken. So the first results were just finding about any induced tree. And then you want to know, can you find specific trees? And from then on, I focused on paths, which was also done in the literature. But you can actually ask for any tree. They say bounded degree tree of this order, a bit less than 2n/d log d. Can you find it as an induced subgraph? It's a natural question, and it was conjectured in this paper by Cooley, Draganic, Kang, and Sudakov that the answer should be yes. You should be able to find this as an induced subgraph. And here, if you want to work on this, I even have a suggestion which method you could use. It's called the weighted second moment method. So again, I said repeatedly that the second moment method does not work for in the sparse regime. By this, I mean the usual vanilla second moment method. But you can actually make it work if you use a weighted version. And that was shown by Dani and Moore for the independence number. So they considered independent sets and show that if you use this weighted second moment method, you can actually prove Frieze's theorem, or even a much more accurate result, not using this concentration thing. You can just do it by a second moment method. And it would be nice to see if you can do this for trees. And I think if so if it works somehow for trees, then it will probably allow you to solve this conjecture of Cooley, Draganic, Kang, and Sudakov. Okay, this is really all I wanted to say. Thank you very much for the questions and for your attention.
Okay, Stefan, thanks a lot for a really nice and very instructive talk. So maybe before we move to the question, I ask everybody who wants to let's give a round of applause to Stefan by unmuting and just clapping. So thanks a lot. Okay. Are there any questions to Stefan?
So Stefan, back to your question number 3. Can you go one slide back? Is it plausible to assume that you can have simultaneously all the bounded degree trees?
A universality here. I mean, it's probably reasonable to conjecture it. They didn't conjecture it, and I think also with the weighted second moment method, it would not follow, I guess. So I mean, I'm just thinking about these results of Richard for normal, say, spanning trees, where you can get all of them. It's always using somehow these 2 rounds of finding something with high probability, some pseudo-randomness, which you then can use for all of the trees at once. I mean, I haven't thought about it, but I would be skeptical. But it might be true, but I think this weighted second moment method will not give it to you, and I have no other idea how to do it.
But you don't have any clear evidence against it, correct?
But I haven't thought about it, so I don't know. Maybe one can even check that it's not true, but I haven't done it. So.
Thank you.
So is it gonna be easier if you don't insist on the right constant in the problem number 3? I mean, if you just say 0.01 n over d log d.
I mean, it will be easier because for paths, we knew from these constructive methods that you can get half of it. So I always think of the path as kind of the easiest specific tree, and they're definitely getting 1 here as a constant is much easier than 2. In fact, it seems like the difficulty only starts when you have 1, and then you want to improve, you want to get rid of this factor 2. For arbitrary trees, I even think just the n over d log d is not known. Yeah, I think the starting point would be to find at least if you give you any. I mean, maybe if you're interested, look in this paper of Cooley, Draganic, Kang, and Sudakov. I'm sure they explain this in the introduction. If I'm not mistaken, it's not known whether you can find any fixed linear size induced tree. Yeah.
I see. Well, and of course you can mix my question with Michael's question to say, I don't insist on the factor of 2, but I insist to be universal.
Sure, but I'm saying even if you find 1, it's yeah, but then you can combine, obviously.
Yeah, no, I'm just saying, like, before shooting for 2, you can shoot for 1 over 100.
Yes.
Maybe universally.
Yeah, I think by the way of comparison, if you take your d to be n over 2, you go to the very different regime. Then a random graph is known to be constant log n universalis, which means it contains an induced copy of every subgraph on constant times log n vertices. Which means I think it's very plausible to conjecture that you do have universality for some constant n over d times log d. Okay. But still, you might want to be more ambitious and to figure out the right constant.
No.
So if there are no more, say, more official questions to Stefan, then let's thank him again for a really nice talk, giving him another round of applause.